this video on stoichiometry. Okay, that's a word that you don't hear every day. To break it down so you know how to say it, it's stoichiometry. Okay, stoichiometry. And what stoichiometry is how to do calculations of amounts based on chemical reactions. And in order to discuss this, we're going to look at parts of section 10.2, molar mass, 10.3, moles of compounds, 11.1, defining stoichiometry, and 11.2, stoichiometric calculations. I suggest you do the following while watching this video. Follow along in the book. The chapter and section numbers are at the top of the slides. Pause the video when necessary to find your place in the book, to listen again to something you didn't understand, or to work on one of the example problems. Okay, the mass of a mole. Okay, we learned before Christmas that the molar mass is the mass in grams of 1 mole of any pure substance. This molar mass, the molar mass of any element, is numerically equal to its atomic mass from the periodic table and has the units grams per mole. So 1 atom of copper would weigh 63 AMUs. 1 mole of copper would weigh 63 grams per mole. Okay. Now, it's important in chemistry that we're able to convert from moles to mass. Okay. So, in order to do that, we basically use the molar mass. We take the number of moles, multiply it by the mass in grams over 1 mole, and that gives us the mass. So, for instance, let's say we wanted to know the weight or mass of 3 moles of copper. Okay, we multiply 3 moles of copper by 63.546 grams of copper over 1 mole of copper, and that would be equal to 191 grams of copper. Okay, our units cancel, and we end up with units of grams. Okay, now, when we're looking at chemical formulas in the mole, okay, we have chemical formulas indicate the numbers and types of atoms contained in 1 unit of the compound. Okay, so 1 mole of carbon difluoride excuse me, contains 1 mole of carbon atoms, 2 moles of chlorine atoms, and 2 moles of fluorine atoms. In order to get the molar mass of that compound, okay, we have to take the molar mass of each element multiplied by the moles of that element in the chemical formula. So if there's 2 moles of hydrogen in the formula for H2O, we add the weight of 2 moles of hydrogen to the weight of 1 mole of oxygen, since there's only 1 oxygen in the formula. The molar mass of the compound demonstrates the law of conservation of mass. So in other words, when the elements combine to form compounds, they don't lose their mass. So for elements, the conversion factor we use is just the molar mass of the compound. And the procedure, actually there's a typo in there. But anyway, it should be for elements, the conversion factor is the molar mass of the element. The procedure is the same for compounds, except that you must first calculate the molar mass of the compound. Okay, now we need to look a little bit at particle and mole relationships in a chemical reaction. Okay. Basically, chemical reactions stop when one of the reactants is used up. Okay. Stoichiometry is the study of quantitative relationships between the amounts of reactants used and the amounts of products formed by the chemical reaction. So, stoichiometry is based on the law of conservation of mass. And if you don't remember what that is, basically the mass of the reactants equals the mass of the products. Okay. The mass, if we summed up all the mass of the reactants and we summed up all the mass of the products, it should be the same. Okay, here's an example. In this case, we have a chemical reaction. 4 moles of iron react with 3 moles of oxygen to form 2 moles of ferric oxide. Okay. The elements and the reactants are iron and oxygen, and the product is iron 3 oxide. Now, we can also look at this being 4 atoms of iron reacting with 3 molecules of oxygen to form 2 formula units of ferric oxide. In other words, we can look at it as atoms in a very small way, or, as you can see in the next line, we could look at it as moles reacting. Okay. 4 moles of iron reacting with 3 moles of oxygen molecules to form 2 moles of iron 3 oxide. Now, if we total up the mass of the iron with the mass of 3 moles of oxygen, we get 319.4 grams of reactants. If we calculate the mass of 2 moles of iron oxide, iron 3 oxide I should say, its mass is also 319.4 grams. Now, when we're going to look at how to calculate the mass of a product or reactant, knowing the mass of another product or reactant in the chemical equation. Okay, remember, if something gets used up, okay, the reaction stops. So we can calculate how much of one reactant would be made or used based on a certain number of or amount of product that was produced, and vice versa, based on a certain amount of product that is that say somebody wants to make. You can go back and calculate how much of the reactants you need in order to make that happen. Okay, and we use something called the mole ratio. Okay, and it's really a very simple thing. I think sometimes people overthink of it, but it's basically the ratio between the numbers of moles of any 2 substances in a balanced equation. And we get it from the coefficients. Okay, we look at the coefficients of the chemical reaction. It gives us the number of moles of different substances in the reaction. And mole ratios can then be used to calculate the moles of one chemical from the given amount of a different chemical. Okay, so an example here, okay, we're going to look at how many moles of chlorine are needed to react with 5 moles of sodium without any sodium being left over. Okay, so we have to have a balanced chemical equation. Okay, the balanced chemical equation says that 2 moles of sodium react with 1 mole of chlorine gas to produce 2 moles of sodium chloride. So, going back to our problem, we know that we have 5 moles of sodium. And we want to know how many moles of chlorine are needed. We take 5 moles of sodium and multiply it by the mole ratio. Okay, what is the mole ratio? Okay, 1 mole of chlorine from the chemical reaction. Once again, only 1 mole of chlorine is needed in the chemical reaction, over 2 moles of sodium, because 2 moles of sodium is indicated in the balanced chemical reaction. Okay, and if we multiply that out, we find out that 2.5 moles of chlorine would be needed to react with 5 moles of sodium. Okay, now, all stoichiometric calculations begin with a balanced chemical equation. Steps to solve mole to mass, and mass to mass stoichiometric problems. 1. Write the balanced equation for the reaction. 2. Determine where to start your calculations by noting the unit of the given substance. If mass in grams of the given substance is the starting unit, you must first convert to moles. If amount is in moles, if the amount of the given substance is in moles, then convert moles of the given substance to moles of the unknown. The end point of the calculation depends on the desired unit of your unknown substance. If the answer is in moles, stop, you're done. If the answer is in grams, convert moles of unknown to grams of unknown using the molar mass as the conversion factor, as we previously discussed. Okay, here's an example. The carbon dioxide exhaled by astronauts can be removed from a spacecraft by reacting with lithium hydroxide as follows. CO2, gas, plus lithium hydroxide, solid, yields lithium carbonate, solid. An average person exhales about 20 moles of CO2 per day. How many moles of lithium hydroxide would be required to maintain 2 astronauts in a spacecraft for 3 days? First, we balance the equation. We need to put a 2 in front of the lithium oxide, or lithium hydroxide reactant, to balance it. 2, we determine the given moles of a substance. Okay? 20 moles per person. 2 people is 40 moles times 3 days, 120 moles of CO2. Convert moles of given substance to moles of unknown. Okay, 120 moles of carbon dioxide times 2 moles of lithium hydroxide in the balanced equation over 1 mole of carbon dioxide in the balanced equation yields, or equals, I should say, 240 moles of lithium hydroxide.